So we only have one more section in chapter 2. It's another chi-square test. This time it's a chi-square test for independence. Basically, I'm going to show you how to do it in the calculator, and then we're actually going to do an example. This is on page 13. We're going to start off with how to do it on the calculator, and then we're going to go through the entire thing. Okay, so first of all, a review. What does it mean for two events to be independent?
The occurrence of one doesn't affect the other.
Okay, the occurrence of one event does not affect the occurrence of the other event. Do you guys remember in the probability chapter how to check for independence?
Vaguely.
Oh, it's like,
It's like
the
probability of this
one or the other is equal to the probability of one and the other.
over something.
So no, basically, is what you're telling me.
Probability of A given B is equal to the probability of A. Right?
Alright, this is the first way to check it. Probability of A given B is equal to the probability of A. Remember the other way to check it? Yeah, probability of A and B is equal to the probability of A times the probability of B. Now, a lot of you guys just use this fact all the time. You can really only use it if the events are independent. So, that's just a review. You should remember that. Okay. So, is this the distribution that you guys have?
Yes.
Yeah.
No, it's not.
No.
Okay.
Oh,
Okay.
it's close.
Okay. I'm going to tell you this distribution is a perfectly independent distribution. Okay. This one is really close to independent. So I went from 50 to 49, 80 to 81, 25 to 26, 40 to 39. So they're not independent, but it's really, really close. And then we have this example. So this is the one I think that you guys have. So let's just say on the piece of paper it says we're conducting a test to determine if there's a relationship between gender and political party. So in this case we have female, male, and then Republican, Democrat, and independent? No.
For Ralph Nader.
Sure. Okay, so we're going to check to see if gender and political party are independent. So this is the distribution that actually happened. This is the distribution that indicates perfect independence. So in a chi-square test, this is going to be the observed and this is going to be the expected. This is what we would expect to happen if the two events are independent, whereas this is what actually happened. Okay, so how to do this in the calculator? Oh, okay, those are not independent, but I'm going to show you why they're not independent. Okay, so this is what I just said. This is what happened if if the events were independent. This is what we would expect. Okay, do you guys remember how to edit a matrix on your calculator? Okay, go to second matrix. Second matrix. Go over to edit matrix A and make it 3 by 2. In that 3 by 2, you're going to put the table that you have. Not the totals, but the 40, 35, 85, 35, 75, and 30. Okay, so again, this is what we observed. So in matrix A, you're putting what we observed. Now go and edit matrix B. In matrix B, you're going to put what we expected. Can you guys read those numbers? Okay, so again, if gender and political party were independent, this would indicate perfect independence. This indicates perfect independence. This is what actually happened. Okay, now go to stat, go over to tests. You all have this test. Regardless of what calculator you have, everybody has this. Go down to chi-square test. So before we did chi-square goodness of fit, now we're doing the chi-square test. Okay, your observed is matrix A, your expected is matrix B. Did you all use A and B? Did anybody use anything different? Okay, let's say I use matrix C. Would you guys know how to get C there? I'm gonna guess no.
Yes, you go to matrix and just click the matrix.
Do second matrix, and then you would hit enter over whatever matrix it is. I don't know if I hit calculate or draw. Okay, apparently I hit draw. If you hit draw, it gives you the chi-square value and the p-value. In a test for independence, you're always going to assume that the events are independent. So in this case, would I reject or fail to reject the null?
Reject.
I would reject the null. So I believe that gender and political party are dependent. They are not independent. Not too bad?
Gucci.
What?
Gucci.
Okay.
I'm sorry for getting
We're fine.
cupcake across the end. I didn't mean to.
Okay. And then if you hit calculate, it's going to give you the same thing. What's kind of nice about this one is it calculates the degrees of freedom for you. You don't have to enter the degrees of freedom. Fun fact.
Do we still have to say that on the when we name the
Yeah, of course. Okay, questions on calculator before we do an entire phantoms. Okay, we're actually going to do the full phantoms just because I think it's good practice. So we're going to look at the demographics of the Titanic. So it says, I'm curious about the demographics of the passengers and crew of the Titanic. Who perished, who survived, and who occupied which lifeboats? How gravely was the tragedy enhanced by class distinction and prejudice? Okay, so then you have this data set that has what class you were in and whether or not you died or survived. So we're going to do the full phantoms, like I said. On the back, there's some other stuff, but you can still write your phantoms on the back, so you can use the front or the back. Do you guys want the good news about phantoms for independence, a chi-square for independence?
Bad news.
Well, there isn't really bad news, but there's
Okay,
good
then
news.
so just
You
tell
want the good news?
Yeah.
Okay, the good news is you skip right to H. There's no P, no parameters. I would have expected us to be much more excited about that. Okay, so we're going to jump right to our null and our alternative. Okay, so we're looking at class and survival. So our null is that class and survival. Survival rate are independent. Okay, instead of independent, some people say not associated. So you could see both. Your alternative is going to be class and survival rate are dependent. Or associated. Okay, you do not have to put independent and the part in parentheses. Choose one. So say independent or say not associated. Don't say both. Okay, can we keep going? Okay. Whoa. Okay, assumptions are the same as the other chi-square tests. They're going to change a little bit how you check them though. So the first one, do we have an independently random sample? Of course it's never going to say independent, but we're just going to say yes, assume so. Do you guys remember the second assumption for chi-square? Large sample.
How is this a sample even though it's just everyone on the Titanic?
We're just ignoring that fact.
Okay. If it's like that on a problem, do we just...
They wouldn't give you a problem like that.
Awesome.
I was just trying to give us something that we actually cared about versus blood pressure.
I don't mind the blood pressure ones.
By the time you got to the 50th blood pressure question, you were kind of over it.
Yeah.
Okay, this is the only part that kind of sucks a little bit, is the way you would calculate the expected values. The expected value is the row total multiplied by the column total all over the grand total. So in our case, there's 8 of these that we need to calculate. I think it's kind of easier to put the expected values in a table. So we have died, and then we have survived, and then we have crew, first class, second class, third class. Okay, so for the crew, the row total is 885. The column total is 1,490. And then I divide by the grand total, which is 2,201. That expected value is 599.114. For a crew that survived, my row total is 885. My column total is 711. And then I divide by my grand total, which is 2,201. You guys see where I'm getting this? Yeah. This ends up being 285.886. First class that died, the row total is 325. Column total is 1,490 over my 2,201. This ends up being 220.014. I don't care that you do all 8. If you do 2 or 3, that's fine. So show me the formula, do 2 or 3 of them with the substitution, and then just calculate the rest. So the rest are 104.986, 192.94, 92.065, 477.937, and then 228.063. Okay, so these are the number of people that we would have expected to die and survive in each category if survival rate and class are independent. So, is the sample large? We're going to say yes. All expected counts are greater than or greater than 5. Okay, next. It's chi-square, so it's always upper tailed, just like the last section. So this is an upper tailed. It's called a chi-square test for independence or a test for association. Again, pick one, don't use both. You're going to see it written both ways, so just know that they're both there. You're going to use the chi-square critical values table. Okay, that means you need to use degrees of freedom. Your degrees of freedom is the number of rows minus 1 times the number of columns minus 1. So in our case, we have 4 rows, so we're going to do 4 minus 1. We have 2 columns, so 2 minus 1. So this is going to be 3 degrees of freedom. Yes, I want you to show that work. Lastly, alpha is 0.05. Okay, T is our test statistic. It's the same as before. So it's the sum of observed minus expected squared divided by expected. So there were actually 673 crew members that died. So you're going to do 673 minus. How many were expected?
I make sure I have the list down.
How many crew members were expected to die?
Oh, 600.
Yeah, we're going to actually use this one, the 599.114 squared all over 599.114 plus, I don't care that you do all of them. I personally did the first one and the last one. So the last one being third class that survived. There were 178 third class passengers that survived. We would have expected 228.063. Okay, you're never actually going to calculate this by hand. You're just going to do it on the calculator. So right now, put this table in matrix A. So put the table of the number that actually did die and survive in matrix A. Do we need me to write down the expected counts again for those of us that didn't write them down?
Yes, please.
Yeah. I forgot to mention this, but you guys know that you're going to have to change the dimensions of the matrix, right?
Is this a 4x2?
It's a 4x2. If you can't remember, put 4x2, and if it's not right, then do 2x4. Okay, remember the observed in matrix A and then your expected in matrix B. Here?
Yeah.
477.937. Okay, and then when you're done, hit draw. I believe you get a chi-square value of 190.401. Yeah. So then it's upper tailed, so you're going to do the probability that chi-square is greater than or equal to 190.401. And if I recall, I look at my sheet, that's about 5 times 10 to the negative 41st, or about 0.
Sounds about right.
Okay, again, like the last time, you have to draw the diagram just what you see on the calculator. So I think it looks something like this. You get a chi-square value, it's probably more like out there, of 190.401. One thing that I neglected to mention before that I would like you to do is I want you to approximately label alpha. So you could do something like this. Alpha is 0.05. Remember that alpha is our rejection region. So our value is within the rejection region, which is why we're going to reject the null. So in this case, you would do 0 is less than 0.05. So I'm going to reject. Okay. Ready to write a conclusion?
Yes.
Can I keep going?
Yeah.
Okay. So we're going to say, based on my analysis, I choose to reject the null. And believe that class and survival rate are not independent. And that should probably be how you expected. I mean, with the Titanic, probably there were more first-class passengers that got on lifeboats than there were third-class or crew members. The probability of obtaining the observed distribution assuming independence is too rare or not rare enough?
Too rare.
Too rare to what?
Just without random chance fluctuations.
Too rare to attribute. Yeah. Too rare to attribute the difference to random chance fluctuations. So what is that last sentence saying?
The chance of getting the chi-square value that we got is way too rare to assume that the null is true, or to believe that the null is true.
Yeah. Did our distribution just happen because it's chance? No, it happened because what?
There's a different, there's a difference.
Actually was.
They're dependent.
Because the two variables are actually dependent. Okay, that's chi-square association test. Not too bad?
Yeah.
Okay, so on one hand, it's nice because you can completely skip p. On the other hand, calculating all those expected values kind of sucks. And you don't actually have to calculate your chi-square value. You just let the calculator do it for you. Okay, this is what you should have on page 14. Okay. So this is Minitab output, so it's just computer output that ran the data. The first number is the number who actually died and survived, what was observed. What's the second number? Expected. So we have observed, then we have expected, and then this last number is what's called the chi-square contribution. So you remember how for each cell we have to do observed minus expected squared divided by expected?
Yeah.
That's what this number is. So this number is the observed minus the expected squared divided by the expected. So what you should notice is right here, so this is where our chi-square value is the smallest. That's where the observed and the expected were the closest. Whereas here, the observed and the expected had a huge difference. At the bottom, you're going to notice the chi-square value, the degrees of freedom, and the p-value. Now, you could be asked, who contributed most to our conclusion? So our conclusion was reject the null. Which group contributed most to that rejection?
First class.
First class who survived, so this one, or really first class in general. So yeah, That's what we just wrote. That last sentence is what I just asked you. So the first class passengers contributed most because 203 survived when about 105 would be expected. How do we feel about this?